Okay.
Let's do the recording.
Yeah. Okay. Sorry, everyone. Thank you for joining us. We're HelioHub. We're a Discord community for undergrads and recent grads interested in heliophysics and funded by the NASA Coffee Drive Science Center. My name is Claudia, and always, I'm joined by my member Dan Zevin of the Space Sciences Lab at UC Berkeley. Um, and just before if you have any questions during this webinar, please feel free to raise your hand, and we'll be happy to answer them as we go. Um, and I'll introduce our guest unless there's anything else, Dan.
I would think if people don't want to ask their question directly, feel free to use the chat function and we'll read the question out loud for you.
Yes, perfect. Yeah. So it's my pleasure to introduce our speaker today, Andrés Muñoz-Jaramillo, lead research scientist at the Southwest Research Institute. Dr. Muñoz-Jaramillo is a solar physicist whose research combines deep learning, data mining and analysis, data visualization, modeling of physical processes, and computer simulations to study the sun. His work focuses on understanding and ultimately predicting the solar magnetic cycle and its impact on solar variability, space climate, and even terrestrial climate change. He earned both his PhD and master's degrees in physics from Montana State University. Prior to that, he completed dual undergraduate degrees at Universidad de los Andes, earning a bachelor's degree in physics as well as a bachelor of engineering in electrical and electronics engineering. Please join me in welcoming Dr. Muñoz Jaramillo.
Well, thank you for the
Welcome,
intro.
welcome.
Okay, so let me share my screen and start. So during the last 10 years now, I have been also living at the intersection of artificial intelligence and physics. And one of the things that I wanted to share with you is one of the directions that I find the most exciting when it comes to using the artificial intelligence to understand the world around us. So, as Claudia said, I'm happy to answer questions if you have them. And if not, I'll show you several things that I want to talk about. But I will be very happy, and I'm perfectly fine with that, if we stay clarifying concepts. So I always like to start my presentations with my take-home message. You know, if you just leave now, this is what I would like you to take with you. And if you stay until the end, this is what I would like you to remember. The first thing is that artificial intelligence is more than a collection of models trained to achieve specific goals. Or it can be more than that if you want. And if you're kind of like intentional about how to use it, how you use it. I think from a scientific point of view, the most interesting aspect of artificial intelligence is that it can use to approximate mathematical functions or relationships or statistical distributions. Basically, the basic concepts, mathematical concepts that we use to describe the universe around us. And one of the main criticisms that is leveraged against artificial intelligence when it comes to physics is that it's a black box. But in reality, if that is how you frame it, you're basically waving away your agency to use it. And so there is always a component of artificial intelligence that is incomprehensible for the human. But you have freedom on what is the nature of that component and where are you going to place it. You can force the machine to give you human understandable quantities. And that is, I think, what I find very exciting about this kind of AI work. Now, the most interesting, for me, one of the most interesting uses of AI in physics is when your architecture is hybrid. You have a machine that is obscure and incomprehensible, but you force it to provide the output to you in physical quantities that you care for and understand. And you combine those with a model that transforms the quantities that you care and understand into what you actually can measure. So that kind of like, and I will show you two main examples of that today. Now, the thing that is kind of cool is that if if you really want to take advantage of this mindset and this framework, you have to step outside of the neural network. So artificial intelligence, a huge part of artificial intelligence is the creation of architectures that enable that approximation of the mathematical reality better and better. So all the development of architectures has been focusing on creating a model that can learn in a certain kind of way to make this approximation. And so when we start using AI for the first time, we typically inherit an architecture, right? We're working with images, so we use an architecture that is designed by others to work with images. Or we're working with language, and so we inherit an architecture that we have as a community found successful and effective when it works with language. But you have more power than that, and that is, I think, the last thing that I would like you to take from this presentation. So let's start with the idea that AI is more than a collection of models trained to achieve specific goals. And so there is this journey that I went through, and I feel that a lot of people go through as they engage with the concept of artificial intelligence for the first time, especially in a scientific context, right? There is the idea that it's like it's a magical tool that can accomplish anything and can solve every problem, right? So that is always where we start. It's very positive and optimistic, right? But you have this kind of like also, especially in the old guard, natural and reasonable skepticism about what this is good for and what it can accomplish, right? Ultimately, well, okay, there is also the idea that is going to be our doomfall, and in some way, this is kind of like a comical idea that is going to trigger an apocalypse, a conflict between machines and humans, etc., etc. But there is also a true, tangible concern that it will replace us because it outperforms many tasks that a human could do. Now the machine can do it better. In reality, it's a tool set. And when we think about it this way, it's a tool set that works for many, 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 many things, and can be wielded in many, many different contexts. And to be proficient in the use of this tool opens many interesting opportunities and offset at some level the apocalyptic view, right? So the way you think about AI is going to change whether AI is an empowering vehicle for you or for us, or it is going to be a threat, right? In this presentation, I'm focusing on this aspect of the tool, which is it's like a tool to gain physical insight or a tool to gain insight about a system. So here at Southwest Research Institute, we had a conversation in my division about how we define artificial intelligence. And I really like the working definition that we arrived at, right? It's a set of trainable mathematical tools that help scientists achieve human or superhuman performance on a wide variety of tasks or satisfy a need. And as scientists, we are particularly interested in those that will enable us to make new discoveries, derive new insights, draw conclusions, find trends, or make current workflows cheaper and faster. This presentation in particular is focusing on the mathematical aspect of artificial intelligence and the fact that it can be used to derive new insights. So the idea of artificial intelligence as a function approximator is super powerful. It's my favorite way of seeing this technology, because mathematics is the language that we use to describe the universe, and all our technology is based on the way we have used mathematics to establish solid conclusions and logical relationships between things. And that's what allows you to, for example, understand the concepts of motion, and apply those concepts of motions to design a vehicle, right? And so there are many relationships existing in our data that we suspect exist but are unknowable and undescribable for us. And so I think one of the most compelling examples will be language. Humans use language to describe the universe, and there is a systematic way in which we ask questions about the universe and answer them. And artificial intelligence has been able to turn language into such a refined and sophisticated statistical distribution that when you interact and draw random words out of that distribution, you get the absolute sense that you're talking with a sentient creature, like entity. But in reality, what you have is a pure randomized draw from a distribution that has been constrained by your prompt and the answer which the machine is giving you. So typically, we have input and output data that we suspect or know for a fact are connected. And there is a mathematical relationship that connects them, but we don't know it. Or it could be something that is absolutely impossible for us humans to achieve. And so that's where we bring these models into the question. You have to have a set of trainable mathematical operations that transform that input into an output. And as long as those have a learnable component, we have proven theorems, mathematical theorems that say that when you have a model with learnable components of an arbitrary complexity, the approximation of the mathematical relationship can be made arbitrarily good. So any artificial intelligence model can be seen as a nested set of equations inside equations, which in code, this is easily just multiple lines of code. So you say A is equal to 3, B is equal to A times 2, right? That's 6. And then you can say D is equal to 2, and C is equal to A plus B. So these kinds of things are like in nested functions. If you throw into this set of nested transformations learnable components, then you can approximate the relationship between your input and output data. All this has to be mediated by a quantification of error. So you have an objective, which is to make the connection between an input and an output, and you have a way of quantifying how close that output is to your physical reality or your objective. And once you have, and this also has to be differentiable. So once you have all this, then you can take derivatives of your cost or optimization or loss function with respect to your learnable parameters and tweak your parameters in a way that maximizes the match between your output and your target. Now, I really like to think about AI systems as being made of an encoding, a latent space, and a projection head. So this set of transformations, you can kind of split them apart this way. So this encoding, you have your input and you transform it mathematically and project it into a mathematical space that we call latent space that has really interesting properties. In the best of cases, this mathematical space, which typically is completely incomprehensible for humans, by the way, but it is very information rich. In the context of large language, when you pass by the encoder, you have what is essentially an internally built dictionary of relationships of the words, of your words with all the other words in your prompt, in your context, and in your answers, right? So, if you have twinkle, twinkle, little star, then you know the relationship between twinkle and twinkle. There is a relationship of similarity, but there is a relationship between twinkle and star in terms of brightness, and right? And then you have little, which has a relationship with star as the idea of size, etc., etc. So now the projection head is the part of your model that takes advantage of this mathematically rich space to accomplish your goal. So in the encoding phase, you put everything into a context, and then in the projection, you use it to accomplish what you want. Okay. Now, when you're applying this in terms of physics, the physics can go in many places. One is, and the one that I'm going to focus on today mainly, is this one. You force your latent space to be interpretable by humans. So you're asking the machine to estimate physical quantities that you care about and understand. You can also have physical transformation. For example, in the case of what I'm going to show you today, the sun is a sphere, but our images of the sun are two-dimensional. So to really get into the reality of what the sun is, it's beneficial to go from a two-dimensional image into a three-dimensional sphere. And so you can have that transformation as part of both your encoding or decoding, projection. And another one, and I'm not going to use this a lot in this concept today, but your optimization function is one of the places where you can also put a lot of your physics. So you penalize the answer for not being physical. So for example, if you're dealing with fluids, you will have conservation of mass, meaning mass doesn't just magically appear or disappear, but if it's entering, if there is a piece of the volume in which you're putting mass in, you have two options. Either that same mass is going out somewhere else, or you're increasing density in that volume. So that is conservation of mass. And if you have an AI system that is producing an answer that doesn't respect this reality, this law of physics, you can put a cost to that. And so that will give an incentive for your model to now adhere to well understood physical principles. So integrating this physics in the design of this architecture is one of the things that I love the most. I'm going to show you two projects that I have been involved with that do this. So the first one is called Arcade, and is related to the idea of solar surface magnetic flux transport. So here you have an image of the solar magnetic field. Okay, this is line of sight magnetic field. So blue is magnetic field that is pointing into the screen, and yellow is magnetic field that is pointing towards you, right? So you have a magnetic field that goes out and in. Okay. Now, if I unroll the sun to produce what we call a synoptic map, it's a 360 degree. It's an approximation to the 360 degree part of the sun, and I advance this very quickly in time. You see that there is like this multiplicity of magnetic regions that appear and disappear. What you're looking at here is the magnetic solar cycle. So sometimes you have lots of them, sometimes you have very few of them. And if you look at this carefully and slowly perhaps, you can see that as time passes, there is a process of transport. So as these regions appear and evolve, they kind of like, let me just pause this so that it doesn't move when I don't want it. So there is this region that was here was much stronger, and it becomes weaker as time passes and spreads around. So this is what we call the process of surface transport. Now we have simulations of this process of transport. This process of transport is governed, or we describe it with a set of mathematical equations. And so it's kind of like understood. But there are like interesting things that we are not able to understand. So the evolution of the magnetic field of the sun, I'm going to show you an equation, but you don't worry, it's a differential equation, but I'm going to focus on it, on the conceptual aspect of it. So the evolution of the magnetic field at the surface of the sun is governed by a diffusive process. So when you have a concentration of magnetic field, it's going to spread out. Okay? So that is one of the main things that happens. And if you have ever seen like this mathematical descriptions of diffusion, it looks like this. It's a second derivative in space. It also has an advective component, meaning that the sun is made of plasma, which is a fluid, and the movement of that plasma will move the magnetic field around. And that term looks like this. You have a velocity that is moving the magnetic field around, and this is, in the context of the magnetic field, is kind of governed by a first derivative. So that's why you have this thing. But in reality, what I want you to focus on is the idea that this is diffusion, so things spread around. Concentration drops. Whenever you have high concentration, it will try to spread around. And then if you have flows of plasma, it's going to have to drag the magnetic field around. And a process of emergence. So when you're looking at the surface of the sun, you see during the solar cycle, there is a lot of regions that appear. And so that's the third component of this process. The idea here is that in our models and simulations of the surface magnetic field, we typically impose a diffusivity that governs the diffusive transport, and we impose a velocity field that governs transport, advective transport, and we, based on observation, prescribe flux emergence. That's the typical way in which we do it. But that means that your flows are not very physical potentially, or they are static, like they cannot react or reflect the physical reality of the sun very, very easily. So the concept behind all this that I'm showing you is, what if we have an AI system that uses a series of observations to tell us what is the best diffusive coefficient, what is the best flow, surface flow, like set of surface flows, and what is the best flux emergence that will describe the model and allow us to forecast the future of the sun. And so in the context of what I was showing you before, we want to accomplish something that looks like, I have the magnetic field of the sun at a given moment, and I want to know the future of that sun. 6 hours into the future is what we actually do in the project. And so what I do is I pass this information to my encoder, and my encoder is going to tell me a diffusivity and a velocity field, okay? And then I'm going to run forward an actual simulation of the magnetic field of the sun governed by that differential equation that I show you, and that will tell me what this future of the sun looks like. And this encoder will also give me an estimation of flux emergence that I need to add to that magnetic field so that I can make a good forecast of the future. Now, when we do optimization, we're calculating a mean error. This MSE is the standard estimation of error that we use in AI, and a maximum likelihood that we're correct. And so this is kind of like a map of the surface of the sun that goes as an input. And then the AI starts estimating flows on the surface. What are the best set of flows that will allow me to forecast that future? And it will also give me a flux. Where is the flux growing, increasing in the surface of the sun? And then based on that, it makes a guess of what the future looks like. And so this is the guess that the machine is providing based on all these kind of ingredients and a simulation. And then this is the target that we wanted to accomplish. Okay, the other project that I wanted to show you is one of three-dimensional emission and absorption. So the sun is a three-dimensional object and is translucent. What you're looking at here is what is on top of that surface. Those regions that we saw that were like yellow and blue are what are giving, remember that it goes in and goes out, in and out. It creates these regions that are like connected in outside of the surface into the atmosphere. And this is the sun in ultraviolet, so it is bright in ultraviolet, and ultraviolet is giving you a sense of the structure of the magnetic field in the atmosphere and the density of the plasma in the atmosphere. So when things are brighter, it's because they are denser, tend to be denser. Now, the sun in ultraviolet is translucent, so it's a little bit like an X-ray. And it has a clear three-dimensional structure. If you look at this part of the movie, you kind of get a very strong sense of there's something that is rotating away. And if you look at this part of the image, you will see things that appear and are rotating in. So it's all, but all our data is planar. It's not three-dimensional. It's planar. And so in this project, we were using 3 satellites that are looking at the sun from different viewpoints to make an estimation of the three-dimensionality of the sun. And the idea is that an image of the sun is the accumulation of light along rays of observation. So when you have a ray that is traveling, all the light that is traveling along a particular path will hit one of your pixels. If that touches the solar surface, it ends on the solar surface. If that is outside of the solar disk, it's going to fly across. Okay? So you have this is a very, very, very nice example in which your reality in what you care about is three-dimensional, but your observation are two-dimensional. But the fact that you have a physical model of how this light is collected and projected into a pixel is what ties all this together. And so in this particular model, you are working with a volume and space-time volume, coordinates of x, y, and z, and time. And your ground truth and your objective is the intensity in ultraviolet for different pixels, right? And so here is kind of cool because you have an encoding of these spatial coordinates that produces ultraviolet light emission and ultraviolet absorption. And then your projection head is a physical model of collecting light and occulting light, like the one that I show you. And that way you can compare to your truth, which is, a calculation of error that also includes continuity. Now, what is cool about this is that what scientists care about is this latent space, both in this problem and in the one that I just showed you. What we want to know is emission and absorption in the three-dimensional volume, which is not something that we have been able to accomplish with artificial intelligence. But now with these kind of models and this way of learning things, we can. So here is the outcome of training a model such as that, where now, for the first time, you can step outside of the ecliptic plane where our instruments are trapped to look at what the sun looks like from different viewpoints and to have a sense of the three-dimensional structure of the solar corona. This project, by the way, was supported by both NVIDIA and Google, and both the NVIDIA and Google CEOs, both the CEOs of NVIDIA and Google showcased this result in their yearly kind of like report on the company. So this gives really interesting possibilities in that now you can use these perspectives of the solar atmosphere that are trapped and limited to the ecliptic plane, basically the plane in which the Earth moves, to synthesize novel views like looking at the sun from the poles. And what you're looking at here is something called a coronal hole. And this is like these dark regions are places where the magnetic field of the sun opens into interplanetary space, and they are a very important source of geospace weather, like the space weather. And so that's why people care. Now, this red line is our estimation of the boundaries of these coronal holes, taking advantage of this novel perspective, compared with blue, which is the estimation of this extent of these coronal holes that you can, the best estimation that you can use if you use a single perspective. So you can see that they're like, kind of like not accurate. So the last thing that I wanted to mention really quick is because we are gearing to start the butterfly project this Friday. So I wanted to talk a little bit about that. Is what you're looking at here is 400 years of observations of sunspots. This is work that I have done with a team of historians that go all the way back to the first observations by Galileo. Okay, so what you're looking at here in the x-axis is time, and in the y-axis is latitude. So, and I'll show you in a moment the movie again so you can see that movie. Well, maybe I can just directly jump to the movie. Let me just start again here. So as you can see, when this movie advances, the amount of regions increases and decreases, but I didn't mention something that is going to become evident as I mentioned, and is that they get closer and closer and closer to the equator. So they start at high latitudes, and as time passes, they get closer and closer and closer to the equator. And at the end of when the next cycle starts, they start again at high latitudes, and they get closer and closer and closer to the equator. So the appearance of these regions is random. There is a stochasticity to them. You cannot predict them. But there is a systematic property of them. They always appear at high latitudes first, when there are a few of them, and then when the solar cycle ends, the few of them are very close to the equator. When the next cycle starts, they're at high latitudes again. And in between is where you have the greatest amounts of them, where you have lots and lots of them. So that can be quantified and visualized in what we call the butterfly diagram, which gives the name to the project, right? So what you're looking at here is every dot that you see here is one of those regions. So there are hundreds of thousands of them in this plot. And each solar cycle is made of one northern hemisphere wing and another southern hemisphere wing. At the top here, I'm just showing you counts. How many of them as a function of time here are in average on the surface of the sun. So this is also one of the things that we kind of like define the solar cycle with. Because we're working with historical data, there is a lot of gaps and missing data. So the background color in this plot is telling you the percentage of observations that we had that year to make this plot. So after 1880, we have like perfect coverage. But before that, there is kind of like spotty coverage. And when we go to historical periods, it's very, 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 very scarce. And it's really cool to work with this kind of data because it's mind-blowing, that we can do science with things, with drawings that were made before a lot of things that we take for granted happened. So at the top of the screen here, I'm showing you some of the historical events that and when they happen in relationship with this data set. The Black Plague happens in this period, and that's why we don't have observations. But we have this, I try to put things from different continents so you can get a sense of how old this goes back. And at the bottom, I have the same, but from a scientific history of science perspective. So, at this time is where we invent differential calculus. At this time is where we disprove the idea of spontaneous generation, basically that germs appear magically when there was the bad conditions. The theory of supply and demand. Here is where we discover the oxygen, the element of oxygen. After 1800s is where we first have anesthesia for the first time, and the theory of electromagnetism happens in the 1880s. And here around the time where we invent differential calculus is when Newton also describes the classical mechanics. And I just want to show you also a little bit of how this data looks like because it's really interesting. So this is more or less an example every 50 years of how we were making these kind of measurements of the sun. So the first drawings by Galileo and his artist friends, I think my understanding of the history of this is that Galileo will ask he had friends who were painters, and he would ask them to make these drawings for him. So he would project with his recently invented telescope, he would project the sun against a wall, and one of his friends will draw. This is extremely modern. The way Galileo and his friends recorded this data is very close as the way we will do it today. But that didn't last very long because paper was very expensive. Galileo did this for 6 months and got bored and stopped. Then what happens is that the sun rotates, as you saw in that movie. And so when one of these objects is here and I look at it the next day, I will see it shifted to the right. And so people said, okay, well, paper is expensive, but the sun is kind enough that it moves the object as a function of time. So I can just take the object and paint it again next day and save a ton of paper. So whereas Galileo will do this one piece of paper per day, this will be one piece of paper per 2 weeks. Then, of course, Hevelius is one of the best observers that we have ever had. And he was meticulous in the way he drew his things. But, for example, we have now, as time passes, people start being interested on other things. And so Schwabe, which was the person that discovered the solar cycle, and there is a question in chat. Yeah, ask Marcel. He was more interested in making sure that he didn't miss any spot, but he was not, because his scientific objective, was to actually see if there was a planet closer to the sun than Mercury. And he wanted to discover it the way we discover exoplanets. He was looking at the sun all the time. He was making absolutely sure that he was never missing a single spot. And so the hope is that at some point, that planet, which he was hoping to call Vulcan, will cross the sun in front of it. He didn't ever find that planet, but he discovered the solar cycle. He did these kinds of observations for 50 years, for 4 solar cycles. Then we finally have the photographic plate. And this is the time where we can now take a picture of the sun every day, and it's okay. And so this is a picture taken in 1859 by the Royal Greenwich Observatory. Now, we still have drawings made by humans even beyond the photographic plate era. So this is a Russian measurement of sunspots made by the Kislovodsk Observatory Mountain Station. But also the Air Force has been making these drawings for a long time as well, the US Air Force. So they look kind of like this. This is now getting back to Galileo level of quality, right? So these are very nicely detailed drawings. And it's really interesting because the scientific goal of different ages have been different things. And for a huge part of the historical period, people didn't even have a clue what they were observing. So people thought that they were like craters and volcanoes on the surface of the sun. So people thought that they were objects between the sun and us. And one of the discoveries or scientific conclusions drawn during the 1600s was that these objects were indeed on the surface of the sun, not in between the sun and us. And of course, if you go to the space era, you can get exquisite pictures again of these kinds of objects. So when you look at these things as distributions, as densities, like if you look at this plot here with the different solar cycles, and in these plots that you have in the middle, like the one I showed you before, there is one dot per object, but they get bunched on top of each other. Like they are not, like these kinds of plots occult density. They become a blob, solid blob of objects. But if you actually calculate how dense these are as a function of latitude and time, you get something that looks like this, like what I'm showing you here below. So you can see that every solar cycle has low density around the edges of the wings and has clumps of high density. And there is a systematic set of properties about these blobs of density. They start high latitude, they go to low latitude, they're kind of like denser somewhere in the middle, and they have blobs that are like more or less towards the center of the wing, etc., etc. And the properties of these wings also change with how strong the cycle is. So if you look at this, the weakest cycle in the last 150 years here, you can see that it's pretty narrow close to the equator, and the wing is kind of like flat against the equator. It's kind of like squashed. But if you look at the strongest cycle of the last 100 years, you can see that it's like a wing that extends very high to the equator and has blobs of density that are larger than those that you were seeing here. And so when you're trying to predict what the sun is going to do in the future, because it's a completely random process, you have to talk about it in a statistical term, in a statistical sense. And the objective of the Butterfly project is to try to synthesize cycles based on the broader characteristics of how strong they are, etc., etc. So the objective of the Butterfly project is to use these observations of the solar cycles that we have to create a synthetic solar cycle generator that has a very high degree of statistical accuracy. And so in some way, what we're trying to mimic is the success of the large language model, but from a scientific point of view. Remember that I told you at the beginning of the talk that large language models are really very, very nuanced and capable statistical models of language, in which drawing random words from them produces an answer that is both useful and recognizable from us as that of another human. And so that's kind of like what we want to accomplish here. So in the context of that schematic that I was showing you, what we have as an input is noise, a random set of noise. And what we want to get out is a denoised distribution, a solar cycle wing, with spots that are distributed in a realistic way, and that those can be conditioned by properties like how strong the cycle is, where in the cycle am I, etc., etc. The way this is done and the way we're going to tackle it is actually more like the way generative AI of images works, right? When you say to the machine, when you go to a ChatGPT for window and say, please make a picture in the style of Picasso of a cat surfing with like sunglasses. And so that what you do when you do that is that you provide the noise, and you provide, I forgot to put here, the conditional information, and then your latent space is that of information loss. So this is called reverse diffusion. So the way we create images right now is by someone like very clever human team is taking advantage of the idea that the destruction of information, if you do it very slowly, is reversible. If you know how to destroy information, you know how to reconstruct it if you do it very slowly. And so that is the objective here. And that is done by using noise as input and predicting information loss. Then you can reverse the action of information loss to get your distribution at the end. And so in the butterfly project, we will be doing this. We will start with a classical approach, but eventually migrate to a generative AI approach. So I think this is one of the things that I really would like you to keep, is that when you're wielding AI, it's very useful to understand how it works, but it's also useful to understand how is it trained, and to understand the fact that not everything has to conform to an existing architecture. You can incorporate your understanding of your physics, understanding of your problem, to force the machine to give you answers in a space that you care and understand, and to take advantage of all the physical insight that you may have into a problem. So when you create these hybrids, you end up with models that have scientific handles that open them up directly to interpretation. So you're no longer hindered by facing an incomprehensible latent space, in some sense what people complain as the black box. Now you put your black box still always there, and that's the power of AI, is that those black boxes are better than us in understanding and establishing relationships. It's undeniable. So to make AI better is not to get rid of the box, it's to put it where you need it. Now, when you incorporate physical models, because scientific models are designed by humans, they are brilliantly elegant and simple and straightforward. Creating AI hybrids results in models that are smaller and cheaper to train than the massive models that we use for general purpose. And you still end up with a competitive model, something that can perform almost as well as the super expensive ones. So you don't need the resources of Google to train these kinds of models if you put the physics in. And it really leans on the idea of approximation, of AI as a vehicle for approximation of reality, a mathematical approximation of reality. And so you really take advantage of the ability of AI, of approximation of approximating mathematical relationships that for a human are just impossible. So going back to my take-home message, and this is the end of the presentation, is what I want you to remember, that AI is more than a collection of models trained to achieve specific goals. Then from a scientific point of view, AI superpower is approximating function. And to wield it properly is not to get rid of the black box, is to know where to put it. That integrating physics into your design enables interesting and compelling AI applications. And the most interesting scientific applications take advantage of physical models and learn and incorporate the physical model in the process of learning. That's it. Thank you. So if you have any questions, I'm happy to take them.
All right. We have a question in the chat from Dr. Janet Lumen, PI of the stereo mission, which you used in your presentation. Janet, I don't know if you want to just turn on your mic.
I see it. I see it.
Hi.
But Janet, you can ask me with your
No,
voice.
I think you'll hear it better from Dan. He has better sound than I have. So thank you for the presentation, though. It's great. Really
Okay, I'm
enjoyed
going
it.
to read it out loud just so that it is also in the recording. So it says, to what extent did your AI tool grab hints from previous research results as opposed to formulating its own approaches? It sounds like you gave it a lot of direction on how to proceed. So when and how does it go beyond what is already known? What if it would have started differently than you initially instructed? Do you bias it or possibly sending down the wrong path? Okay, so there are several questions here to unpack. So one of the powers of AI when you train it with data is that it can learn context from the entire body of data in a way that we cannot do when we use human design, like human interpretable models, right? To give you an example, for example, there is this thing that solar physicists do with ultraviolet images to try to estimate density and temperature using ultraviolet images for every pixel, right? So humans typically do this pixel by pixel. And every pixel is done completely independent of its surrounding pixels. So there is no context information because that's the limitation of the human created model. When we do the same job using AI, we can make that estimation of density and temperature based on a pixel and its surrounding pixels. And that allows the machine to identify structures that are not necessarily identifiable from a single pixel, but when you use the vicinity, you can. And so all these models that I was showing you are taking advantage of that context. And not only that, within an image, but also within multiple images. The sun has a lot of cell similarity. Active regions look a lot like themselves, whether they happen in 2010 or they happen in 2025. So the machine can learn to recognize, oh, I have seen this before, and infer the density and temperature using the ultraviolet information, taking advantage of the fact that it recognizes a structure that is bigger than 1 pixel and that it has seen it before. So in this context of what I showed you, Janet, it was desirable that the machine takes advantage as much as possible from recurrent patterns in the data. Now, it was our implementation of the physical model that takes advantage of previous research results. So when we work with either the tomographic reconstruction of the corona or when we are doing surface flux transport at the surface of the sun, surface magnetic transport, we are using radiative transfer models or surface flux transport models that are very well validated and established within the community. And so it was not the AI that used the previous research result, but it was us in the incorporation of the way we traditionally model these kinds of systems. And so we did intentionally give it a lot of directions into how to proceed, because ultimately what the machine is doing is making estimates. So we, in the context, for example, of flux transport, what we're actually asking the machine is, given these last observations of the surface magnetic field of the sun for the last 24 hours, what do you think are the governing plasma flows that will make it evolve into the future? That's the question that we're asking, right? And so the fact that we're forcing the machine, the only way the machine can control the evolution of the system is by providing flows. And then those flows are used to drive a perfectly transparent simulation of solar magnetic fields. And so that is kind of like where you really put the constraints. Same happens with the tomographic reconstruction of the three-dimensional corona. The machine can only control the output or the generation of the synthetic ultraviolet image through the allocation of emission and absorption in a three-dimensional structure. But that has to still work when you run a radiative transform model to create the synthetic image. And so I really like to think about this is like you have a car, right? And the car is your scientific model. And you have an agent. And your agent can, and you ask the agent, I want you to go from point A to point B. But that agent can only influence the trajectory of the car using a very specific set of inputs. In the case of the car, it will be a steering wheel, an accelerator pedal, and a brake, right? The machine cannot magically move the car. It has to conform to a physical reality where the only way of moving the car around is by using a steering wheel and the accelerator and the brake. And so it's the same here. We instead of putting the black box around the entire system, we say, okay, the box is here, and this box can generate flows. And it's the only way in which the machine can evolve the surface magnetic field of the sun into the future. Now, the randomness in initialization of an artificial intelligence model is something that we typically account for. And so I didn't go into a lot of detail, but it is part of how we estimate uncertainty. An artificial intelligence model will train slightly differently if you show data in different orders. And it is subject to some decisions that you make in the way you optimize it, which data you train it with, etc., etc. And so in both these projects, we follow kind of like standard practice into evaluating how the model would look like if we show the data, different data, or if we show data in a different order, etc., etc. And that creates what we call an ensemble of models that we can use to assess confidence and uncertainty. So every single one of these models is confident, but when we look at them as a group, we see where they diverge. And that's how we can assess rogue outputs. So, yeah. That answers your questions?
Kind of. There's a lot there. One thing, if you want to be lazy and you want to let the machine do as much as possible, if I gave it your movie of evolving synoptic maps, would it figure out how to do that on its own without knowing about the physics of the surface flux transport?
There are models that allow that possibility. So that is a possibility. But they then become only useful from a purely practical point of view, right? So the idea that we want to understand the system itself as scientists makes those models less attractive. If we were focused only on space weather forecast, then models that do the whole end-to-end thing and just we give them an input and they give us an output are desirable and may be actually highly performant. Like one of our inspirations was a climate prediction, like terrestrial climate prediction, space, like weather prediction model. So in this moment, the best terrestrial weather prediction models are end-to-end AI systems. So these are developed by Google and IBM and things like this, where these models now outperform any model that we have ever had. They're completely opaque. They're like an entire black box from beginning to end. But when we are in the business of forecasting weather, nothing beats them right now. But the inspiration that we drew is a model that uses an actual flow transport of winds. And it is not the best model. It doesn't outperform the Google model, but it's competitive. So if the Google model is having like 99% accuracy or whatever 7 days into the future, this model will have 95. But the attractive aspect of this from a scientific point of view is that it gives you estimations of flows. So it measures flows in the atmosphere. And you can do science with that kind of things. And so, personally, I'm more interested in the family of models that are smaller, maybe a little less performant, but open up completely to the scientists new ways for understanding.
Great. Thank you very much. It's really, really a new world.
Yeah.
Thanks again.
Yeah, so glad you're with us, Janet. Thank you.
Yes.
We have some more questions in the chat. Umar, yours was first. Do you want to read your question yourself?
Yeah. So I was curious about like what the current use of AI actually deployed systems like and systems used by the NOAA or NASA are looking like, because I'm assuming that it requires a lot of like formal verifications and a lot of testing for, these AI models to actually make a lot of big decisions.
Yeah. So in this moment, none of the, I would say, like governmental forecast uses AI systems in terms of NOAA and NASA. So, I mean, NASA doesn't do forecasts. That has never been NASA's goal. They have a team that does pseudo-operational forecast and sometimes use it internally, but they don't put make forecast public. So internally, they may have forecasting capabilities, but it's just for NASA consumption. Like public-facing space weather forecast is all done by NOAA. And they don't use AI systems yet because there are very strong, as you imply in your question, they are very stringent. There are two reasons. There are very stringent requirements of reliability, is one. And the second one, their stakeholders are used to receiving information in a certain kind of way. And so that plays into that doesn't necessarily take full advantage of AI systems and etc. and how they can produce forecasts themselves. And so it is definitely something that kind of like lags behind what an industry forecaster will do, which doesn't have the same requirements and the same kind of like mandate. And so yeah, so that's the answer to the question.
Thank you.
Right, and hope I'm pronouncing this right. Donan, feel free to ask yourself if you'd like.
So have you considered using GAPA as an evolutionary framework to like optimize and evolve like the parameters of new predictive models? It's like a new framework and it's different than like traditional AI systems, but it works with like the same principles. So I was wondering if you've seen or looked into that.
I have personally never used it, and I'm not familiar with it. You know, as you describe it, and correct me if my interpretation is wrong, But what you're describing is a specific technique for optimization. Is that a correct statement?
It's a technique to like create new models and then like test it against data.
So there is, when you're training an AI model, you're relying on a very kind of a very specific form of optimization that also has received and is continually receiving attention and development, right? To cast AI models to incorporate something like what you're describing, you require a certain degree of compatibility in the optimization process of AI. And so, I cannot give you a good answer right now of whether this framework will be compatible with the way current models are trained or not. Um, it also is possible that the evolutionary framework that you're describing, if it has any connection with like genetic algorithms for crossing models and obtaining better and better models, that this may rely on the assumption that you can generate many, many, many models. And that is not something that is easy to do when you're using AI models that have a lot of parameters. And so, there is like a set of limitations. When you're working with AI models, you tend to work in a computationally starved environment where your computational capability is typically your biggest resource constraint. And so you cannot train many models, for example. You can only train one or two, or you have to be clever in how you train it so that you can use different like a part of your evolutionary of your training as different realizations of models. And so that would also make it potentially incompatible in terms of cost. But, without me looking in detail about, I have worked with genetic methodologies for fitting models, but they were very small models compared to what typically you have in AI. So there may be an incompatibility here. Now, small models are always much more interpretable, and you're totally correct. And so these hybrid models that I was describing are kind of like a way of accomplishing something that is in between. Instead of having a fully enclosed, super complex models that you can understand, you break it into pieces with this idea of the encoding and decoding. And even though the training process and the optimization process is still computationally limited, you produce now things that are directly interpretable. So bottom line is that depending on the models that you're working with, there are different optimization processes that will be compatible with the restrictions, but the objective of interpretability can be made compatible in both contexts. You just have to work within your limitations and within your kind of like design paradigm and strategy.
I see. Thank you.
All right, it's well past the hour, so I'm gonna definitely stop the recording, and also that sometimes generates more question or gets people motivated to ask a question. So we're willing to stick on for another minute or two for additional questions. But right before we end the recording here, let's just give another round of applause for Andres for his generous time in this fascinating topic. And I hope some of you are going to continue with us on this journey with the Butterfly Project, starting tomorrow, I believe. Yes.
Yes.
And so Claudia, myself, Phoebe, Andres will all be there. We hope some of you will be there as well. That's going to be some exciting to see many of you contributing to some of these results. All right. So again, thank you, Andres. This was definitely worthwhile. Very, very fascinating. I still have a lot of questions in my head, but we're going to end it here. So thank you, and we'll see you later on.
See you.
Bye-bye.
Bye.